Hello, everybody. Welcome to this afternoon's, this evening's session of ADAS. In fact, I should use the often mocked Australian phrase that was just made for online conferences. G'day. My name is Nuri Laurenti. I'm from the AAO at Macquarie University, and I'll be chairing this session for today. Behind the screen here, we also have Peter Toybin and Yuji Shirasaki as a room manager, help desk, and backup chair. And of course, we have Francesco and Jose Enrique, who are perennially present as members of the LOC and making everything work. So I hope you have a good session, everyone. Our invited speaker first up today is Eugene Magnier from the University of Hawaii Institute for Astronomy. He's the lead of Pan-STARRS imaging processing pipeline. And he will be talking today to us about the Pan-STARRS imaging processing pipeline, the lessons learned, and looking forward. Thanks very much, Eugene. You have the floor now.
All right, thank you very much. Good morning, good day, whatever the appropriate phrase is at this particular time of night. I'm glad to be here, and I appreciate being invited to give a talk on this, although I feel a little odd because I'm talking to what I know are a group of people who are all working on the cutting edge of software and exciting technologies for the future. And we at Pan-STARRS are more like a big old battleship. We have a very solidly stable and long-running code base at this point. It feels strange to say that, but it's been running for a decade with a very stable set of code. So we're looking forward to future developments, and I'll talk about a little bit how we've done things in the past and some future developments we'll be looking towards going forward. But let me first start off by talking a bit about Pan-STARRS itself. I know people have heard about Pan-STARRS some, so I don't have to necessarily do too much description of it, but it is started off with one telescope, PS1, which has 1.8 meter telescope with was at the time the world's largest astronomical camera with 1.4 gigapixels, covering a 7 square degree field of view. And we've been doing some significant surveys with this telescope. The first incarnation of Pan-STARRS was the Pan-STARRS Science Consortium, which formed to operate that telescope for a period of what ended up being about 4 years. And one of the major projects from that was to survey the 3 pi of the sky, the 3/4 of the sky visible from Hawaii, that's North Pole down to -30. And with many observations, and then to build up a nice deep sky, static sky collection, that's the image that we see here, and measurements of objects across the sky from that. And at the end of that period, we eventually planned and worked together to get a release of the data to the mast. Our first data release back in December 2016 was static information. It was the stacks, it was the average properties of objects, about 3 billion objects in that data release. And then in the beginning of last year, we had a data release which was the dynamic component. So now you can go to mast and you can get individual exposure pixels. Actually, they're warped, but that's not really relevant. And you can get the light curves from the 3 billion objects that we've observed. So there's about 120 terabytes of data in a searchable database there. And one of the challenges that we found was trying to process the photometry calibration for the sky with such large dynamic range, ranging from low density at the galactic pole to super high density fields in the bulge. And we needed to be able to handle all of that. And the database calibration system did a pretty good job of that. So since 2014, Pan-STARRS has had a new incarnation. We continue to use the telescope in kind of the same sorts of ways we've observed before, surveying the sky. But now our funding comes from primarily NASA, with some additional collaborators who are interested in some other topics. NASA wants to find the killer asteroids, and they've been tasked by the US Congress to find all of the, or some 95% completeness of objects larger than 140 meters by the end of the 2020s, so by 2030. We'll see if we'll get there, but Pan-STARRS has been a major contributor to that. What time we're not using for doing the NEO discovery, we're trying to catch some of the interesting transients, the supernovae, the LIGO counterparts, ice cube counterparts, and so forth. Just as a quick touch base on what we do with the data, we get about 800. Oh, sorry, I meant to mention the other aspect of the incarnation now is that we have a second telescope, Pan-STARRS 2, which is essentially, in all ways, a duplicate of Pan-STARRS 1, except that in every important detail, it's actually different. It's the same size mirror. The camera is essentially the same, but lots and lots of the construction and everything are basically different. So we effectively have two different telescopes that we have to support. And this telescope now has what is the world's largest astronomical camera, at least in terms of pixel count, until LSST gets their camera in place. PS1 had 60 detectors, PS2 has 64, so that makes it a little bit bigger. We get about 800 to 1,000 exposures a night, sometimes up to 1,200 from those two telescopes, and we have to process all of them. This is an embarrassingly parallel operation because every single exposure can be treated more or less independently. In fact, every single one of those 60 or 64 chips can be treated independently at certain stages. And so we have a large cluster that we own and control dedicated to the processing of the data. We have to get our data out on short time scale because we have to serve our asteroids to the asteroid community by the mid of the next day so that we can get follow-up observations. And so we have to go through an entire sequence of telescope observes the sky, individual exposures get processed, individual exposures get little chunks pulled out of them so that they can be stacked or differenced against things, and we can find moving objects as difference detections. So then eventually we can pass on difference detections to the moving object pipeline. Here's a little flow chart that shows the way data flows through our system, and I'm not going to go into this in detail, but one point here is that the image processing pipeline that I'm responsible for with my team of a handful of postdocs, we've got 3 postdocs and staff scientists, we're responsible for data up to about this level. There are people in the outside world, transient teams, and inside the IFA, the moving object pipeline team, who are trying to take the things that we detect and turn them into discoveries, whether they're supernovae now or asteroids that might blow up the Earth in some way. Those are the science products that the teams that are not part of the IPP specifically, although some are part of the IFA Pan-STARRS team, some are external collaborators. And also when we ship out these, when we've done these data releases, that's been done through the Pan-STARRS system, through the IPP system, and then some other subsystems as part of the Pan-STARRS team. We take a bunch of exposures. We've been operating for 10 years now in the main surveying process with the operational telescope for one telescope, and 2 years now for the second telescope. By this time, we've gotten about a little over 1.5 million exposures, which, because we have a large camera, accounts to almost 6 petabytes of raw data. We actually store 2 copies. That's neither here nor there. We have just geographically distributed data across 2 different islands. So the asteroid, when it comes, won't wipe out one cluster and all of our data. We, just for reference, when we process the images, one of the stages that we process them through is to detect objects in the images and do PSF model fitting for every object. And at this point, we've done 1 trillion measurements of stars through that process between all the exposures and multiple reprocessings of exposures. So the Pan-STARRS data analysis system has been pretty heavily tested over the years with many, many observations, many, many repeated measurements, and we've attempted to calibrate those measurements as best we can. At this point, we have about 16 petabytes worth of data. You can't see that because of this funny thing there. About 16 petabytes of data sitting on our cluster, and we have one of our data management problems is simply tracking all of the files that get generated by this process. We've got about a database, MySQL database that tracks billions of entries on our disk, so we know where they are and can find multiple instances of the same effective file. We keep replicated data so that we can avoid data loss. And so that's one of our interesting challenges, and that's been working pretty well with a simple but pretty robust hardware for our MySQL database. We also use a second MySQL database just to track the processing stages. Every step that gets performed is tracked through that processing database so that we know where in the sequence anything's been finished and what needs to be done at any given point in time. And that model of querying a database for what comes next has been quite successful as well. So our current mission is to discover the killer asteroids, and Pan-STARRS is currently the dominant telescope for doing that. This is showing Pan-STARRS in pink taking on the role of being the dominant hazardous asteroid discoverer for the asteroids that the US Congress wants to find. That's the ones larger than 140 meters. Anything smaller than that is not quite globally catastrophic or even quite continental scale catastrophic, more local. So this is the scale where we worry about that being important on the scale of countries being impacted largely. So right now we're discovering about half, a little more than half of all the hazardous asteroids of that scale that get discovered in the world. But we also discover supernovae, and here's a plot that shows our presence in the Supernova Discovery world. We have 2 telescopes now, so we're a little bit higher than we were before. There was a bad year here, but one of the big changes recently has been the arrival of ZTF. And one of the things that is an important challenge for Pan-STARRS is that we discover faint things compared to our competitors, both in the asteroid as well as in the supernova business. So the Catalina is the main competitor we have, and they discover fainter asteroids. This shows the supernovae. ZTF and Atlas are the teams that are discovering with a smaller set of telescopes the brighter asteroids. And so we are doing really well with discovering things that are faint. But one of the challenges is that people will need to follow up on these things. Somebody needs to go and get a spectrum of a lot of these supernovae, and so people tend to go after the bright things. So if you look at not just the supernova alerts, but if you look at the actual confirmations from spectroscopy, the picture changes quite dramatically. First off, only about 11% of all of these supernovae from all groups are actually classified. You'll notice the scale has gone down to about 200 from over almost 2,000. And we lose out heavily in this business. So one of the things that the IFA is doing right now to try to do a bit better job in the faint end and to more automatically follow up some of our candidates is to roboticize the UH88-inch, the 2.2 meter telescope, so that we can more rapidly turn around the spectroscopy and control the follow-up a bit better for our candidates. It's a big challenge, but it's going to be even worse in the era of LSST, who are going to be dominating down in the 21, 22, 23 magnitude range. So there are some interesting challenges that are not software, because it's not a problem of discovering the supernovae, it's a problem of following up. So there's problems that we will have to address in the future there as a community. But one thing this does say is that you want to have very pristine collections of objects, of candidates coming out. And so one of our things that we need to work towards is making sure that the things that we discover are well characterized, and so that we know what are reliable things to waste large glass time on for spectroscopy. For the future, going forward, we're going to continue following up NASA's mission of finding hazardous asteroids, but we also are looking towards new options for doing some interesting science. And so one of the things we'd like to do is to be able to get, is to help out with this problem that Euclid has. So Euclid is a satellite that's going to be doing dark energy and dark matter studies with a combination of weak lensing and spectroscopy. Their weak lensing process is to have a very high quality measurement of shapes to measure the weak lensing. But in order to do the three-dimensional tomography of the universe, they need to have redshifts to objects. So they need to get photometric redshifts for about 1.5 billion galaxies. They need 8 color photometry. They need 5 optical-ish bands in YJH. Well, they provide YJH, but they don't have on their satellite UG, RI, or Z. So they're one of the only satellite missions that I know of that need a ground component. And the ground component from somebody needs to be available to provide photometry to these 1.5 billion galaxies across the sky. They're concentrated in the anti-galactic, away from the galactic plane, high galactic latitudes, and away from the ecliptic plane. So LSST will do surveying of the south and provide the photometry sufficient for the south. In the north, it's not clear what exactly they were thinking, but we have stepped up with some others to help fill in the gap. The Pan-STARRS 3Pi survey that we released over the past couple of years covers a larger part of that area, but it's nowhere near deep enough. Euclid needs photometry 2 magnitudes or more deeper than the Pan-STARRS 3Pi survey. So this is in the south also currently reasonably well covered by the dark energy survey. But in the north, there's a big hole. So we formed a collaboration with a team from Canada, France, Hawaii telescope called CFHT, the Canada, France Imaging Survey, who have been trying to get U and R band photometry for Euclid. And we are going to provide I band photometry since we continue to survey the sky, and some Z band. And G band comes potentially from Subaru and potentially from a telescope in Spain called the Alhambra telescope. And we're also recently have been joined by a team from Japan that is called Wishes that are going to be surveying much of the area in Z band as well, because Z is really hard. So we naturally survey the sky looking for our asteroids. We have to survey the sky in I band during bright time. So we naturally cover a lot of the area that Euclid needs photometry for. So we will naturally get I band coverage of the areas that Euclid needs to cover by about 2023. Z band has been slow, but now that the Wishes team has come in, they'll take the north half of this part of the sky, and we've done this region, and we'll be doing the section between 30 and 38 degrees declination. We've internally had a Unions DR2, and we're going to be doing internal releases before Euclid is ready for getting our full data set. And eventually when Euclid receives the data, we'll around that same time in the 2022-2023 time scale, we'll be doing public releases of this data set. And one of the things that's really critical about the analysis of this data is that we need to have high quality photometry. The photometric precision that we have from the 3Pi survey is great. We're really happy with it. It's been a mainstay for people now for a couple of years for good quality photometry across the Northern Hemisphere. However, to get to the photometry necessary for the Euclid mission requirements, it's probably going to need a little bit of a boost up. We're going to need to do a bit better job of calibrating out some of the systematics. So that's one area where we need to improve our photometric analysis so that the reprocessing will be at a base level good enough for the improved calibration. So one thing I want to touch on, I'm not sure how much time I have left at this point, given the later start. I wanted to just mention that one important aspect of the way we've designed the Pan-STARRS image processing pipeline is to be flexible about the camera. It's basically camera agnostic. We have configurations that define some aspects of the camera, and once those are defined, many different cameras can be used and can be processed through our system. And as an example, I've been doing a survey of variability in the Andromeda Galaxy using data from Pan-STARRS on the right, from the Hyper Prime camera, and from Megacam from CFHT over years. And I have processed this data all with the same pipeline, and I can choose configurations appropriate for the Andromeda Galaxy for this type of data for all 3 cameras, and then process them all in a common framework so that then I have the same measurements, I have the same kinds of parameters for every object, and those data sets can be merged together in a seamless way to provide a single internally consistent set of data. Here's examples of the Andromeda Galaxy, density of stars and Pan-STARRS, CFHT's Megacam, and HSC. And the density in the Andromeda Galaxy in these different cameras varies a lot because of the different resolutions and the different depths. So being able to process those same data sets with those different data sets with the same processing system takes a little tweaking, but it's working quite well now. Looking forward, we don't have so much to do in terms of software management or software infrastructure. What we need to do improvements on are our algorithmic improvements. Our overall infrastructure for managing the processing and managing what we need to do and doing the overall data structures and so forth, that seems to be pretty robust and has been running for a long time now. But there are aspects of the analysis where we don't handle instrumental signatures that our somewhat esoteric camera throw at us quite as well as we should. So here's an example of a galaxy that's gotten completely hacked up by corrections that we have to make in our camera because of some persistence that exists in the camera, and some low-level bias variations that are a little inconsistent across individual cells. And so because of that, we're not doing as well in large-scale galaxy photometry as we'd like. So some of our development needs to be fine-tuning our algorithms to somewhat better handle our esoteric instrumental artifacts. We'd also like to do a bit better job with galaxy model fits that we do. We do some somewhat abbreviated amount of effort on the galaxy models, and we could do a bit better job with the now that we have a larger cluster of computing resources available. Another thing that I'll talk a bit about more in a moment is difference image garbage rejection. Our mainstay these days is to discover asteroids and supernovae in difference images, and we haven't really changed our algorithms in our difference image processing for 10 years, and a lot of development has happened in that regime, both in terms of doing a better job of the image matching and the image differencing, as well as in doing a good job of trying to classify the things that come out. And as I mentioned, we need to do a bit better job on our photometric and astrometric calibration. So in terms of garbage rejection, we can address—
You have 5 minutes, Eugene.
Thanks. We can address some features at the instrumental level, and we are working to do a better job of rejecting things as an instrumental signature, such as crosstalk structures, and we even want to do a better job of subtracting out bright stars. This is Arcturus, the star that used to lead the Hawaiians in their canoes to Hawaii. It's also the star called Hokulea. And we don't do a great job of modeling the surface brightness of very, very bright stars, but we can do better with that. So we're looking forward to that as well. But garbage rejection, we use some, in the asteroid search, we use some statistical cuts based on crude parameters from the images to reject things that might be garbage, but we rely very heavily on human vetting. Every morning, humans have to examine lots of objects, lots of detections. In the supernova game, we throw machine learning at some of the stuff. This is actually the team at Queen's University Belfast, part of our external collaborators. And they have some interesting machine learning algorithms that they've been using for garbage rejection. They've gone through 2 iterations on this, but they still rely on huge amounts of human vetting to classify tens of thousands of objects per week. So we would like to try to do a bit better pushing some of that machine learning into the image processing pipeline to try to include a little bit more statistics that can possibly help to reduce the garbage from all these other sorts of features. But we're realistic that machine learning doesn't always get you the answer, and we probably will still rely on human eyes for a while. So conclusions, we've been running for 10 years pretty solidly. We've processed huge amounts of data, and our archival value to the community is quite large between the images for people to do finding charts in the sky and photometry as a reference. We've had some interesting, I think we've had some successes in the way we've developed our software in terms of making everything instrument agnostic, and the way we've designed the management of the processing through tracking everything in a database. And actually our analysis code has been designed from the beginning to be very carefully thought through in all the stages of the analysis. The future plans, I mentioned, we have to do some work on artifact suppression. We'd like to do a better job of machine learning garbage reduction. We have work to do on better photometric calibration, mostly driven by improvements for Euclid. And we'd like to do a better job on how we do shape analysis of galaxies, maybe being able to do better weak lensing measurements from our data, which we don't currently do. And I will stop there.
Thank you very much, Eugene. Are there any questions? Please put your hand up on the Zoom, or put your question in the talks channel of the Discord. Well, let's start with a comment from Nico Vermas, who awards you an ADAS 2020 quote award for, quote, Anything smaller than that is not globally catastrophic, just locally catastrophic, unquote.
That's our mission motto.
Any questions, please? I know it's early for some.
I have a question. Well, it's just an observation. Sounds to me that,
Please,
you know,
Sergio.
just to filter out the garbage, you need to push more into the machine learning, maybe deep learning as well. I'm not sure. I'm not really an astrophysicist, so I'm a software engineer. So, but it seems to me that there is, with your huge data set, there is some possibility that some of those models will be successful, I guess.
Yeah, I think we're pretty hopeful that with enough manpower, brain power on the on training things, we could do a much better job. There's been a fair amount of work at Queen's on training the machine learning to recognize things based on the training sets they've got. But I'd like to, I think that if we can push it a little earlier in the processing before the difference detections, that we might be able to supplement the data products with the classifications that we get at the individual exposure stage. And that might help with the classification a bit as well. To be honest, we're mostly labor limited. We're a very small team, so we're usually just chasing fires. Trying to expand these machine learning experiences has been, you know, it's a little slow with the small team we got.
Thank you, Eugene. Next, if we could have a question from Thomas Jürgens.
Yeah, thanks for taking my question. Eugene, if you could go back, please, to the artifacts, the CCD artifact slide. I'm rather surprised to see bleeding there, and I'm rather surprised to see actually CCD artifacts after 10 years, what you said. So that's an easy to fix thing, right? CCD artifacts can be taken care of, right? I need a couple of test runs, and then I characterize my CCD, and essentially I have a model for it, and then I'm done, right? So I'm really surprised.
You would be surprised what our detectors are like. So these are features that come from various things. There's persistence that's pretty bad. So we have to actually identify stars that would provide persistence, and then because we have to be heavily filter out things for faint sources that might be garbage. We have to model out and subtract off the bleeds the persistence that is retained. There's also this is a particularly bizarre case because I think this is actually a case where we threw in data that was a range in our exposure times that were not particularly well characterized by our dark models. So it's a bit of an exaggeration here, but we do have some features in our cameras that you don't usually actually have to correct. We have 4,000 some individual cells in our camera, and each one of those cells is essentially a separate camera. So each one has its own features. Interesting.
Yeah, but that's not a big problem, right? I mean, that's what CCD astronomy does every night, right? You identify the defects, the problems, and you correct for them if you can, and otherwise you just reject the image.
Yeah, we reject a fair amount of our pixel area because it's uncharacterizable, and there are aspects where we have the levels, the faint level, like I mentioned, there's a nonlinearity at the faint end, and the nonlinear at the faint end and the persistence are the two of the main problems that we have. There's also an issue that is a correlated readout problem that we have to subtract off that is difficult to model in a reliable way. We haven't seen too much of the Starlink satellites, although I guess they must be there. I see the comment in the chat. We have a lot of little glints and things that come in, and so we automatically try to filter out some long linear features like that, and that may be suppressing some of the Starlink satellite effects for us.
We also have another question from Carson Fulls, who says, can you describe quickly your image differencing algorithm?
Yeah, it's a variant on the Allard-Lupton method, but it is a cross-convolutional process that was more or less described by Yuan and Akerlof 2008. So it's basically, we solve for a target that's the least worst, least bad between two different, in the generic case, when things are elongated in ways that are in opposite directions, that you can't convolve one star to the other. We try to convolve both images to the appropriate least bad target. Alternatively, it will choose one direction or the other if one of the images is clearly better than the other. But it's basically Allard-Lupton.
Thank you. Are there any more questions? If not, let's thank Eugene again in whichever way we can. And we are now going to break for around 15 minutes. We will restart at 1/4 so at 6:45 UTC. Oh, sorry, that was my bell to say kill the speaker. So we shall start at 6:45 UTC with the next talk, who will be Sergio Pintaldi. Thanks very much.
Was Stephen's question answered?
I just saw that question. Shall I answer it verbally?
Yes,
Yeah,
please
sure.
answer Stephen's question.
Sure. So our cluster is basically about, I'm forgetting the exact number of cores, but it's about in the range of 5,000 cores. And we have two classes of machines. We've got large storage machines, which do some local computing, and we have additional thin compute nodes that have just CPUs and not much storage. We've got a hosting arrangement with the university in their IT cluster. They have a compute facility that is relatively cheap for hosting costs for us. And so our costs for maintaining that cluster are pretty low. And we tend to actually buy used hardware, which really brings down our actual cost of purchase. And so every time I've tried to spec out anything in the commercial cloud world, I've been scared off by both worrying about reliability, latency. Basically, we need to be able to rely on the data getting into our data system and being processed on a short time scale, because we have to have everything out every night. And also just the cost has looked astronomical to us, no pun intended.
Thanks, Eugene. Gabrielle behind has, not sure if it's a question or a comment or an asking for more details about persistence artifacts removal. Do you see that question? Object masking, persistence artifacts removal, object masking while line and column background gradient subtraction.
We do some things like that. I'm not sure what the question is, though.
Yeah.
We have one stage of our processing, we have to subtract on each row a model of the background, because it kind of bumps up and down due to this crosstalk problem. It's actually sort of a trend across each row. And that's kind of ugly. It only has to happen on some of our detectors, though, or some of the cells of our detectors. We also have to effectively match cell by cell backgrounds because of this low-level nonlinearity that we can't seem to get a good handle on. And so that ends up causing problems when there's bright things like large galaxies that bias that in ways that the algorithm can't handle.
Mm-hmm. And there is a very timely question in the chat if you already see Starlink satellite effects on the images.
Yeah, I was trying to answer that earlier. Yeah, they don't kill us certainly yet. And I haven't heard complaints from the MOPS, the moving object folks who are vetting the images about what they are doing, how many they see of those. But some of our filtering of long linear features may be removing some of those.
Okay, thank you, Eugene.